Good morning and welcome to the first lecture of the new year. So we are switching to a new topic, the last topic of the course, which is actually fault tolerant control. Today we will provide an introduction and we'll describe one approach that is called model matching. In particular, apart providing an overview describing the structure of fault tolerant control approaches and describing the model matching technique, we will also provide some notes on how to apply these to the 3 tanks benchmark that we have seen in previous lectures. So when designing a fault-tolerant control system, we start from some assumptions. Well, the first is that we already have a closed-loop control system, and we have a plant for which we have a model that is either continuous or discrete time. So we're not considering discrete event systems here. And in healthy condition, this control system is fulfilling some control specifications. For instance, it can have some desired phase or gain margin. It can have some desired rise time, overshoot, steady state error. And we assume that at some time, t0 that is unknown, we have a fault. And this fault is possibly known or unknown, but what we want is that even in the presence of this fault, our control system is fulfilling another set of control specifications, and this set is still acceptable. So the ideal condition is that the set of control specifications we can fulfill in faulty conditions is the same as the one we fulfill in healthy one. That would be the perfect fault tolerance situation. But in practice, due to limitations in the sensor and actuators available, it is not possible to fulfill the same set. But even if we fulfill a set that is reduced, well, this should be still acceptable. And what acceptable means depends on your application. So it can simply be that you don't have any catastrophic failure, nobody dies, or it can be that still your system can operate in a profitable and economic way. So you may remember this figure we had from one of the first lectures, where we were presenting this concept of the set of attainable behaviors in the case of healthy and faulty system. We were assuming that we have a system with one input variable and one output variable, such that we can make our drawing in 2 dimensions. And so this is the set of all the input-output pairs that you have in healthy condition, because this is the intersection of the set of the behavior that the system allows when in open loop, and this is the set of the behavior that we have for the controller, for in the closed loop case. And so the intersection was this one. And this is inside the set of specifications, so we are happy. The problem is that when we have a fault, this set B0 gets transformed to this other set. So we are in this condition. And so what happens is that now we have this intersection between the possible behaviors of the system in faulty conditions and the behavior that you can have when coupled to the same controller. And the bad thing is that this part here is outside the specifications. So to make this fault tolerant, we would like to accommodate the fault by, in this case, changing the controller. So we have a new controller with new sets of possible input-output pairs. And what we get is this new intersection. Let us use a different color now. And this is inside the specifications, the original specifications, so it is something that we can safely use. From a pictorial point of view, this one is smaller than this one, and that was made on purpose. So probably in faulty conditions, the set of behaviors that you can attain is smaller, is limited. So maybe you don't get the best performances as you got here, but still they are acceptable. And so the entire part we are going to cover today and in the next lecture is how to follow, how to implement this blue arrow. So how to accommodate the fault. There are anyway two families of fault-tolerant approaches, one that is called active and the one that is called passive. So the active one is the one where you first have the diagnosis step. So you diagnose the fault, and based on the diagnosis, you accommodate the fault. And you do this by changing the control law and or the set of actuators and sensors that you're using, such that you reach one of these three cases. The original specification are still fulfilled. That is the ideal case. So that would be the green set here is still equal to the blue one we had here. Or we have a reduced or different set of specifications that are fulfilled, but still they are some way okay. And we call this graceful degradation. And indeed, this is the case. So this green one is smaller, but still inside this big set of specifications. Or if you can't reach any of these, at least you want to guarantee safe conditions. So you probably have to stop to operate your system. Think about a self-driving car. When something is wrong beyond the possibility to accommodate that, at least you want to stop safely the car such that you have no accidents, nobody is injured. So this is called fail-safe. So in our example here would be probably to reach some point here that is outside the specifications, but it is safe, let us say. So this is the origin, so you have 0, 0, so you apply no control to your system, and your system has a 0 output. So if the output is the speed of the car, so the car is stopped. You can't accelerate, you can't decelerate, you just stay there, stop. It is safe. You don't fulfill any specifications, but you don't kill anybody. On the other side of the spectrum, we have instead passive fault-tolerant control approaches. The passive fault-tolerant control, you don't need to do the diagnosis. So you don't care for the information about which fault is present, because you're not using that. In a passive approach, you are following one of these two sub-approaches. So either you have a control that is adaptive. So you don't know what happened, but the control is able to adapt in a transparent way. And indeed, what you may have encountered as adaptive control is doing that. So you have a control law that by definition continuously adapts to changes. So if you follow this course, you know what I am talking about. And I will not go into details because anyway, we are not covering this now. So there will be another lecture where we give some notions about this. But the idea is that if you have a fault that is slow, it is developing slowly, you can track it and adapt your control law smoothly to that. The problem is that this is not going to work if you have a complete loss of functionality. So if something completely breaks down. So one possibility could be a situation where you have a sensor that has an offset that is growing from 0 to some non-zero value slowly. And you have a control law that can compensate for that offset. The situation could be depicted like this. Let us assume that over time, this is the actual output that the sensor should measure. And this is what your sensor is measuring. So slowly it is drifting away from that. So what you see here is an offset. So if this is slow, you may have a way to compensate for that, to identify its value. And you can continue to operate. But if at some point your sensor completely breaks down, then there is no way. So you have no more information here. There is nothing you can do. Another family of passive approaches is to design a control law that is robust and can tolerate by itself a certain category of faults. Indeed, in robust control, this is what you are doing. So you can consider a fault as one possible variation in the model, and you can design a control law that is robust to that variation. So we will not provide anything about that in this course, but you can have a look at this course on robust and multivariable control design. So the idea is that this is robust to small changes, but the problem is that the performance that you get is a trade-off. So this control law is not optimized for the healthy situation. It is something that works well both in healthy and in faulty, but it is not optimal in any of these situations. So it depends. So if you have some system that needs to be really, really performant, then this is not the way to go. Okay, so we will cover initially active fault tolerant control approaches. So now we have an entire section about this. The overall scheme of an active fault tolerant control approach is this one. So you have some familiar components that you anyway have in a control system. So you have your controller and a plant, and they are in closed loop. So this is the loop you always have in a control system. And then you have an extra loop here that is added in order to implement the active fault tolerant control. And this loop consists of a diagnoser, the thing that we already covered in lectures 5, and a supervisor, which is the new part, that is affecting the behavior of the controller. So the added loop that you see here is using information from Y and U and using that to close the loop here. So the diagnoser in particular is computing a fault decision, so isolating the fault and estimating the magnitude of the fault. So these two things together means you identify your fault. And once you have this information, you use that in the supervisor to produce a new set of parameters, theta c, that affect the behavior of the controller. So as an example, if you have a controller that normally is like this, so it is a simple output feedback. So you have minus k that multiplies y. Then in this case, k is described by this theta c. So you see that this kind of control is parametric and it is parameterized by the gain k. So k is the one that you want to change in order to adapt and accommodate a fault. So the knowledge of how to do that is included in the supervisor. So the supervisor is the one that knows for every possible faulty condition how to produce a new theta c, in this case a new gain k, such that in those faulty conditions this controller still stabilizes the plant and allows for some acceptable performances. So basically the supervisor is an algorithm that can design a controller, and that is parameterized by this information. So all the supervision loops is including fault diagnosis, as we said, and this algorithm to alter the control law. And we said this alteration is described by a new parameter vector that we call theta c. And this theta c can be of two categories. On one side, it can be a simple index that selects one out of a number of possible controllers. For instance, we can have the situation where we have n faults, and for these n faults, we have n different controllers. And this would make sense. So you can have one behavior when everything is healthy, then you can have one behavior when one sensor is faulty, and then one when another sensor is faulty, and so on for all the possible components. So this makes sense if the faults that can occur in your system, they always occur in the same way. So they can't be big or small. They are either there or they are not. So in this case, you have a limited number of possible faulty behaviors. And for this limited number, for each one of them, you have one controller that works. So this is the idea about switching controller. So you pre-compute a controller and you just select which one you need to use. But in general, a fault is described by a magnitude, as we have covered in the previous lectures. So it is unfeasible to have as many possible controllers as all the possible kind of faults you can experience. They are infinite in principle. So you need to redesign your controller. So that's the only way. So theta c can contain coefficients that are used to redesign the controller, as in the example that we made before. So theta c contains the parameters that make up the gain of this simple controller here. So the idea of controller switching, seen pictorially, is this one. You have all the possible controller, you have your plant, you have the diagnosis and the supervision part, and this is selecting which one you want to use. For instance, at some point in time, you are using here controller number n. So of course, there are pros and cons with the two approaches. So this requires less computation power at runtime. So your embedded controller can be simpler because everything that had to be computed for control design was already computed. You just need to store, and you just need to be able to isolate which fault is present, such that you know which controller to switch in. But of course, we said the drawbacks are that here you can only account for some limited number of faults. On the other side of the spectrum, we said we need to redesign this controller online. So the pros is you have more flexibility, you get better performances, but of course you need more computational power on board on your controller. So now that we introduced the different kind of fault tolerant control and the main architecture that is used, we can look into the details of one technique that from an academic, a didactic point of view is interesting, but in practice, its usefulness is limited. But anyway, let us start with that. And this is model matching. So the idea of model matching is to redesign the controller such that the closed loop system that you get in faulty situation is the same as the one you got in healthy situation. So from the point of view of what occurs from here to here, it is the same. So from the point of view of what reference you give to your system and what is due in the output of your system, the two situations are going to be the same, which is really ideal. So if we can do that, the fault is not affecting your performances. In practice, instead of an equal to, this is going to be an approximately equal to, and we will see why. Okay, this is the main idea. In practice, we have some limitations. So this is working for linear systems. And it is working for linear system when some geometrical conditions are met, not always. For nonlinear systems, actually, there is no guarantee that this is going to be possible. But let us see how it is going to work and when it is going to work for linear systems. So we are assuming to have the following continuous time linear dynamics for the healthy system. And we assume to have this state feedback here now. This means that in closed loop, the dynamics are this one. So these are the closed loop dynamics. Now, a fault is going to alter the open loop dynamics of the system in this way. So the matrices that we had before, A, B, and C, will become some faulty AF, BF, and CF. So being fault tolerant in this case would mean that the closed loop dynamics stays the same. And the closed loop dynamics depends on this, A minus BK in the healthy case. So you see that we have A minus BK here. That's the state matrix of the closed loop dynamics. And in the faulty case, we have AF minus BFKF. So AF and BF, they depend on the fault. So we have no control on them. But what we can do is to change K. So the gain of the matrix. So the gain of the controller. This is what we want to change. We want to get a new controller gain such that this is holding. And if you look at that from a geometrical point of view, you can do this, you can solve this problem only if B and BF have the same image, that is, the same column span. This makes sense. So if you look at here, so you want BF, KF to, let's say, go the same places as B and K from a geometrical point of view. Because if you can't do that, it may be possible that there are some poles of A that you can no longer move to where you want. So as an extreme case, think that BF becomes 0, completely 0. You can easily see that whatever you choose KF, this is never holding, unless for the very unlikely case where AF is already equal to A minus BK. But that's really unlikely. In all the other cases, this product is not going anywhere. It is stuck to 0. And indeed, the case where BF is equal to 0 is a case where they have no the same image. So the image of BF is just the number 0 in this case. But having the same image means that either your actuators are all working, possibly not a great weight, but all working, or you have redundant actuators. That's the only way to guarantee that they have the same image. If this is not the case, still you can settle for a reduced goal. And the goal is that instead of having perfect equivalence here, you have approximate equivalence. So you want these to be not too far away from this one. And the way to translate these into a rigorous mathematics is to minimize the norm of the difference. So you have one matrix here minus this matrix. You take a matrix norm. You want these to be as small as possible. And for this, there is actually a solution, because this is a sort of least square optimization. And you can solve that by introducing a new kf, which is obtained by computing the Moore-Penrose pseudo-inverse of this matrix BF. So you have BF pseudo-inverse that multiplies AF minus A plus BK. So you can try yourself, take this solution, replace that here, and you will see that this is going to minimize this norm of the difference. And remember that the pseudo-inverse that we have here is actually written out as this. The reason we need the pseudo-inverse is that usually B is not square, so we can't just take the inverse. And the computation you do is this one. So you still need anyway to compute a matrix inverse, but this is B transpose, so this prime is transpose. BF transpose that multiplies BF, you need to take this inverse and multiply by BF transpose. So you need these to exist. This is the condition that you need. And so you see, it depends just on the matrix, the faulty matrix P. So in the extreme example I made before, where BF is 0, well, this is not invertible, of course. So you can see that in the case where you lose all the actuators, of course, there is no way to be fault tolerant. And there is actually nothing you can do in that case. So that was anyway a general case. So let us focus now on two more specific cases. The one where we have sensor faults and the one where we have actuator faults. So we start with sensors. So we have the healthy dynamics here. We have an output feedback controller, and the closed loop dynamics now is this one, which depends on these matrices. So the difference with before is that as we don't have state feedback but output feedback, you have also the C matrix here in the product. The fault is changing the open loop dynamics this way. So now you have A and B, they stay the same. The only thing changing is CF. So this is modeling some fault in the sensor. So the way you're modeling it here means that you can have a gain fault in the sensor, or that you can have some sensor that is completely dead. So this means that one row of CF is 0. This is the case corresponding to a sensor completely dead. So what we want to do now is to design a new control law where we just need these to hold, because the other matrices are anyway the same. So you want these to hold. And now the geometric condition is only on the matrix C. So you want the kernel of CF to be not bigger than the kernel of C, which is another way to say that even when your sensors are faulty, they are still providing the same information as in the case they were healthy. So information can be some way distorted, or you can have one sensor that is completely dead, but you had another one that was providing the same information. So this is what can happen. You can also see this by considering that the kernel is the orthogonal complement of the raw space. So think about, so you take C, you multiply C by X, this is your output. So you see that from a geometrical point of view. Or you can just remember that the kernel is the vector space for which C multiplied by your state is 0. So this is the vector space of all the states that will cause the output to be equally 0. And this is the vector space on which basically you don't have information, because everything there will provide the same output, 0. So you cannot tell what is what. So normally, your sensors are not going to provide information on everything, but you don't want to lose further information when you have the fault. This is a way of looking at this. So if this is holding, you can find a solution for your KF. And the solution is KF equal to what you have here. The original K multiplied by a matrix P. And this P, again, is obtained by computing some pseudo-inverse. So in this case, you have C that multiplies the pseudo-inverse of CF. So you can check for yourself. If you replace these here and here, you will see that this is a solution. Again, you need this product here to be invertible. So if you want, you can further reason of these on this requirement and be sure you really understand that. And also you can check yourself, it is just some simple algebra, that this one is a solution. So it's useful because then you can see how things really work, and it's probably easier to understand. Okay, the other specific case would be when one actuator is faulty, one or more actuators are faulty. So we start from the same open loop dynamics, the same control law, so we get the same closed loop dynamics, but now the fault is occurring on the matrix B. So the closed loop dynamics in the faulty case is this one. So now the dynamics is described by this matrix, A minus BFKC. In the healthy case, you had A minus BKC. So this is the one that you want to be equal to this one. So as everything else is the same, this translates to this requirement. BFKF should be equal to BK. And now the geometrical condition that we have is the same that we had before. So we want the image of B to be contained in the image of BF. So basically we want BF to be not, the image of BF to be not smaller than the image of B, which means the actuator still have the same control authority. They can still do the same things. You can make BU going the same places, from a geometrical point of view. And the interesting thing is that this condition is a sort of dual with respect to the one we had for the sensors. And please notice that in this case we have B multiplying K, and now the condition is on the image of B. So B is on the left. But here we wanted K that multiplies C to be the same. So we have C on the right of this product. And you know that the matrix product is not commutative. So in this case, you get two different conditions that are basically one the dual of the other. So you have one condition on the kernel of C here, and you have one condition on the image of B here. So from this point of view, it can be easier to see why you get these kind of conditions. And you have this kind of duality. So said this should not come as a surprise that the solution is this one. So the new gain Kf is equal to this matrix product n that multiplies K, where n is a matrix that you compute. So previously you had K that multiplied P, K that multiplies P, duality again. Now we have something on the left that multiplies K. And n is computed using a pseudo-inverse again. So you have the pseudo-inverse of Bf that multiplies B. In the previous case, you had Cf, C that multiplies the pseudo-inverse of Cf. So they are switched as well. So there can be some mnemonics how to remember these solutions. Okay, again, as a useful exercise, think from a geometrical and practical point of view what this condition means, and you can just check that this is a solution by substituting this in the closed loop dynamics. Okay, and that was the model matching. So you can see that the model matching is providing a direct way of computation for getting a new gain for your controller. So based on what are the faulty dynamics, you directly compute the new gain. So this is one of the cases where you do controller redesign. You are not switching between available pre-computed controllers. And the computations you need to do, they are not extremely complex unless you have a system that is really, really large. But for something with a practical size, computing that, even on an embedded platform, is not that big issue. Also because you just compute it once when you have a fault. You don't need to compute every time step, unless your fault is evolving. But the problem is everything that we did here was analytical pen and paper and based on the very big assumption that we know BF, we know AF, we know CF. That is, we exactly identified the faulty dynamics. And as well, we have an exact model for the healthy dynamics. So we have some sort of perfect knowledge. This is the big limitation, because when the model that you identified in healthy and faulty conditions is off with respect to the reality, it may be that this is not going to do the trick. So it is like when you design a controller and you try to do a perfect zero-pole cancellation. It works pen and paper, Probably it also works in simulation, but in reality it is not going to work. It is not a robust way of designing a controller. And this is pretty much the same thing. You want to perfectly cancel out something, pen and paper, assuming that you exactly know the dynamics. In practice, this may not work. So you can still use that, but you need to do some analysis and some simulation, some extensive simulation, and check that for all the possible combinations, and check that for all the possible combination of uncertain knowledge of the healthy dynamics and of the faulty dynamics, this is still going to stabilize your system and provide reasonable levels of performances. So you need to guarantee that. Okay, so we are going to end this lecture with providing some useful information about how to implement this approach and other approaches we're going to cover in the next lecture on the example, the 3 tanks benchmark. And the obvious issue that you may face is that this system is nonlinear. But the model matching approach and the ones we're covering in the next lecture, they are designed for linear systems. So I want to be sure that you remember how to linearize this one, and you don't get stuck into this step, such that you are able to focus on designing a fault-tolerant controller. So please remember that linearizing means that you start from some nonlinear dynamics like this one, which are written in terms of states, input, and output variables that we denote with a subscript NL for nonlinear. So these are the variables describing the nonlinear dynamics. And please, please remember, they are not going to be the same variables that you use when you linearize. Why? Because when you linearize, you are approximating this nonlinear differential equation with this one. So first of all, you need to start from an equilibrium of the system. So you need to have a triplet x0, y0, and u0 such that the dynamics f computed in x0 and y and u0, it is equal to 0. So this is an equilibrium, okay? And y0 is the output that you get in this equilibrium. Well, in this case, then you can approximate the derivative of x and L by taking the partial derivative of f with respect to x and L itself when x and L is equal to x0. You multiply this partial derivative, which is getting you the rate at which this is changing with respect to x, and you multiply that by the difference between the actual x and L and the linearization point, the equilibrium x0. So that's the whole idea of linearizing. So you approximate a function let us draw it in terms of x and L. Why this is green? So you have this function. Let us assume that your linearization point is 0. Okay, so when you linearize, you are taking tangent. Oh, this didn't really work, but let us assume it is a straight line, okay? Okay. So you approximate a value here as this tangent multiplied by this increment. So this is x and L minus x0. Okay. But this function depends on 2 variables. So if you know the rules of differentiation, then you need to add the partial derivative of f with respect to u and multiply it by u and L minus u0. Okay. The same thing for the output, but now as y0 is not necessarily 0, you need to remember that what you're approximating is the variation with respect to the equilibrium. So it is ynl minus y0 that is approximately equal to partial derivative of g with respect to x computed in x0 that multiplies this change of x plus the same with respect to the change of u. So here basically you would also have minus x0 dot, but this is equal to 0 because we are in an equilibrium condition, so you can just forget that. But please remember that it should be there. Okay, now the idea of linearization is that you take these two equations, they are now linear with respect to these variations. And so you can write these linear dynamics, but the very important thing is that, remember, you're writing them in terms of new variables, in terms of this, and this, and finally this, not in terms of the original variables. That's the thing that a lot of students got wrong. So the dynamics you're writing is the derivative of this delta x is equal to a delta x plus b delta u. And delta x is this one, delta u is this one. And similarly, the delta of the output is equal to c delta x plus d delta u. So delta x is this difference, delta u is this difference, delta y is this difference. Please remember that. Said in another way, from a pictorial point of view, it is like saying that when you have your nonlinear system and you have your input u and the output y, this is the u and l, and this is the y and l that we had in the previous slide. In order to approximate that with a linear model, you need to take u, subtract the linearization point input, and you get the delta u. This is producing through the linearized model delta y. And if you take your delta y and you add back y0, the linearization point, you get y. And now you can compare this computed with the linear system with this computed with the nonlinear system. If you don't remember to subtract this and add this back, the things you get here, they are completely off. Or you can also see the same thing from the other point of view. You can take delta u, feed it to the linear model, and you get delta y. But to delta u, you need to remember to add back u0. You get u. You can feed that to the nonlinear system. You get y here. You remove y0, and then you get a delta y computed using the nonlinear system. So these two are not going to be the same, but the difference there is just due by the dynamics that you neglected because of the linearization. So this seems trivial, probably you already know that, but just to be sure that you don't get stuck just because of this. Okay. So this lecture, we provided an overview of fault tolerant control approaches, and we went into details about the model matching method. So in the next lecture, we are going to cover other two active fault tolerant control approaches for linear systems that are called the virtual sensor and the virtual actuator method, that are similar to the model matching, but they don't need the same strong geometric assumptions that the model matching method needs.